This video is about optimization. Hopefully by the end of the video you'll be able to state the meaning of the term optimization, use differentiation to give an optimal value over a specified domain, and relate maxima and minima to optimal values in real life examples. Let's start with the definition. So the optimum something is the most favorable point, degree or amount of something for obtaining a given result. We'll have a look at what it means in this example. So you're asked to find the maximum area of a rectangle inscribed in an isosceles right-angled triangle whose hypotenuse is 20 centimeters long. So in this case, the optimal value is the maximum area of the rectangle. Now, there's a set way of solving optimization problems which involves 4 steps. So we'll go through each step individually and relate it specifically to this problem. The first step is to draw a accurate and labelled diagram which represents the problem that you're dealing with. It's important to label unknown parts of the diagram using variable symbols which you can then put into equations later on. Here we're going to draw a right angle triangle and we're going to draw a rectangle inside that right angle triangle. We're going to make sure that the length of the hypotenuse represents 20 centimeters, labelling all the angles, and finally we're going to label the unknown quantities. So this height is going to be y, this length is 20 centimeters, that's the hypotenuse, but the width of the rectangle is unknown, and so we're going to label that x. Finally, we're going to say that this little bit here is 10 minus x, that's half of the length minus x, and that's the same as y because it forms another right angle triangle. We're then going to label that the area of the rectangle is x times y. The next step is to identify the optimized quantity, write it as a function in terms of a single variable. You then need to determine the domain of your function. Here we are looking for the area, and we can write that area in terms of the variable x. The reason we're able to do that so easily is because of our well-drawn diagram, well-labelled diagram. Finally, we're going to set the domain of x as 0 to 20. For step 3, we're going to find the derivative of the function and determine for which values it's 0. You also want to find the values of any endpoints, and these form what we call critical points, and we analyse them in the final stage. So we're just going to differentiate this down to 10 minus x. We set that to 0 and we find that x equals 10. The final stage is to analyse the stationary points and endpoints to find out which value of your variable fits the optimised function. In this case, we were looking for the maximum area. So we start off by doing a second derivative test. Find that the second derivative is minus 1, and that tells us that x equals 10 is a maximum because the entire second derivative for all values of x is negative. We'll analyse a0 and a20, and both of those are equal to 0, which tells us that x equals 10 is the absolute maximum, which means it's the maximum value that x can be. The question asked us to find an area, so we look for the function a where x equals 10, and we find that the maximum area we can create is 50 centimeters squared. So these are all the steps that we've just used. It would be worth writing them down so that you can make sure you remember them. That's the end of this video, but you need to go on and watch the next video, which is going to be the worked examples from this section.